Hey everyone, I'm going to teach you the first half of our acids and bases unit today. So this is unit 10 and this PowerPoint is on Google Classroom if you would like to go through it at another time. All right, so first of all, let's go over some definitions and properties of acids. So acids have a tart or sour taste. So you can think of lemon or vinegar. Like citric acid is in a lot of citrus fruits. Vinegar contains acetic acid. Milk, you've got lactic acid in milk. There's just a lot of common acids that we have in our home. It's not just the dangerous ones that you think about from our chemistry class, like hydrochloric acid or sulfuric acid. So some acids, like the ones I just said, are dangerous. They will burn the skin. This next bullet point that you see here with the brackets and the hydrogen in the middle, this is how you annotate the concentration of something. So if you put brackets around it, that means the concentration. And in this case, this is hydrogen ion. So that's something that acids are known for. That's a common definition of an acid, is that it donates hydrogen ions to another substance. So in a solution, if the concentration of hydrogen ions is greater than 1.0 times 10 to the negative 7th, then that means it is an acid. So in this example that you see here, we have acetic acid plus sodium chloride yields sodium acetate and hydrochloric acid. So you can tell by comparing the reactants to the products what the acid is. So on this side, this compound here starts with a hydrogen, but on the product side, you can see that acetate no longer has that hydrogen. That hydrogen ion was donated to chlorine on the other side of the equation. So since this compound is donating protons, or it's donating hydrogen ions, that means it's an acid. So you might have noticed that I just referred to hydrogen ions as protons. That's another thing you're going to hear a lot in your acid-base unit. If you hear an acid referred to as a proton donor, it's the same thing as saying that acid is donating a hydrogen ion. Now in this example, you might be looking at both of those and saying, I don't think either one of those is an acid. But again, you have to think of it in terms of our definition, which one is donating a hydrogen ion to the other. And in order to determine that, we have to look at the product side. So this NH3, once you get to the product side, it's NH4, which means it gained a hydrogen from water, which means water lost a hydrogen. Now on the other side of the equation, it's just OH negative. So we would say in this case that water is acting as an acid. It is donating a proton or a hydrogen ion to NH3, which is ammonia. All right, so those are acids. Bases would basically be the opposite. So rather than having a sour taste, bases have a bitter taste. So if you've ever tasted baking soda or even soap, or if you've ever had to take a chewable antacid, you might remember that they all had bitter taste. So that's characteristic of a base. Now, in the same way that soap, when it's wet, is slippery, that is another characteristic of bases. They are very slippery. If you've ever had to wash your clothes, you might have noticed if some of that strong detergent gets on your fingers, it's really hard to get it off. It takes a lot of hot water. That's that slippery feeling of a base. So bases contain OH ions, hydroxide ions. So you can see in this example that calcium has the hydroxide, but on the other side of the equation, it has lost the hydroxide and now magnesium has it. So you can think of a base as having hydroxide. On this side, this is the base. On the product side, this is the base. Now, another definition we have for bases is that they are proton acceptors, or they accept hydrogen ions. So in this earlier example that we looked at with ammonia and water, remember we said that water played the part of an acid because it donates that hydrogen to ammonia. Well, ammonia would therefore be a base because it is accepting that hydrogen from water. So acids are proton donors, bases are proton acceptors. Now, when you have a neutral solution, that means that all of the hydrogen ions and all of the hydroxide ions are equal to each other. So there's an equal amount of acid and base ions. So water and an ionic salt are the products when you have a double replacement reaction between an acid and a base. You can see here that hydrochloric acid, when mixed with sodium hydroxide, yields water and salt. All right, now earlier, when we were talking about acids, we said that their hydrogen ion concentration had to be greater than 1.0 times 10 to the negative 7th. So in this example, it's saying identify the solution as acidic, basic, or neutral. So this is saying if the hydrogen ion concentration is equal to this number, is it acidic, basic, or neutral? Well, if you plug this number into your calculator and put it in standard notation, that would be the same as 0.01. Whereas 1.0 times 10 to the negative 7th, which is the number we used earlier that represents neutral, if you put that in standard notation, it would look like this, 0.601. So which of these is a bigger number? It's this one. So since this number is greater than this, then we would say this is an acidic solution. Now in this second example, the hydrogen ion concentration, if we were to put this in standard form, then this decimal would be moving to the left 8 times. So since there are 8 digits behind the decimal, then you would see that that is smaller than this neutral number, the 1.0 times 10 to the negative 7. So since it is smaller than that, we would say that this is not acidic, this is a basic solution. So I know this is kind of confusing because when we see a 2, we think, doesn't that mean smaller? But it's the fact that it's negative 2. Negative 2 is bigger than negative 9. So in these 3 examples, you've got acid, neutral, base. Okay, remember, think of this number as 10 to the negative 7. All right, in this next example, it says 25 milliliters of 1.5 molar sulfuric acid is added to 25 milliliters of 2.5 molar potassium hydroxide. Is the resulting solution acidic, basic, or neutral? Well, in this example, you have equal amounts of your acid and your base, but the concentrations are different. And rather than using these numbers with a 10 to the negative something, we're just using our normal concentrations that we learned about in the solutions unit. And you should be able to tell that 2.5 is a bigger concentration than 1.5. So the fact that we have equal volumes of an acid and a base, but the base has a greater concentration, means that your resulting solution will be basic. Another thing that plays into this problem is the fact that sulfuric acid and potassium hydroxide are a strong acid and a strong base, so they will completely ionize in water. Okay, so new terms. We just learned about acids and bases. New term is conjugates, conjugate acids and conjugate bases. So you might have noticed on the other side of the equation, on the product side, after the acid has lost a proton, on the other side of the equation, it now has become a base. And what was once a base on the product side of the equation has now become an acid. So I'll show you an example of that in a minute, but let's just look at these definitions. A conjugate base is what remains after an acid loses a hydrogen ion. So it will now be a product. And a conjugate acid is what remains after a base gains a hydrogen ion, and it will also be a product. So in this example, this is an example of acetic acid mixing with ammonia. So you can see that acetic acid on the right side of the equation, it has lost its hydrogen. So this is our acid, we can tell because it donated a hydrogen. So we would say that acetate is the conjugate base of acetic acid. Okay, so this is the acid and this is its conjugate base. Whereas ammonia is a base, but on the right side of the equation, after it has gained a proton or gained a hydrogen ion, it is the conjugate acid. Now, if that's confusing to you, think about if we were to go in reverse. If we were to take the product side of the equation and go in reverse. Now, ammonium ion would be donating a proton to acetate, and therefore it would become ammonia. So it's acting as an acid. And acetate would be accepting a hydrogen ion from ammonium. So it would become, since it's accepting, it's going to become a base. So acids, their new form is their conjugate base, and bases, their new form is their conjugate acid. Now in this next example, you can see that HF, which we know is hydrofluoric acid, has lost its hydrogen ion on the right side of the equation. Now it's just F negative. So that means this is our acid and this is its conjugate base. Water gained a proton from hydrofluoric acid. So water is acting as a base, and then H3O, which is called hydronium ion, you're going to see that a lot in this unit. H3O plus is called hydronium ion. It's just the acidic form of water after it's gained a hydrogen. So anyway, what I was saying is water's a base, hydronium ion is its conjugate acid. And in this last example, this is going to be a little bit more difficult to see. But if you look at, let's look here first, H2SO4. Where do we see SO4 on the right side? Here we go. This SO4 now doesn't have any hydrogens. So that means this is our acid, and this is the conjugate base. Whereas HCO3 gained another H, so now it's H2CO3. So this is a base, and this is its conjugate acid. Notice that in this example, we're ignoring sodium, because sodium is going to end up being a spectator ion. It really doesn't play a part at all in this reaction. So once again, this is our base, NaHCO3, and this is its conjugate acid, H2CO3. Sulfuric acid, this is our acid, and Na2SO4 is its conjugate base. Now, like I said, that's our first lesson. Now you're going to do some bookwork problems on page 474 of your book. Note that on number 23, I just want you to label the acid, the base, the conjugate acid, and the conjugate base. Another thing I want to tell you about is your interactive reader. If this is at all confusing to you, then I wanted to tell you the pages in your interactive reader that you might find helpful. We are in chapter 14. So in your interactive reader, that's page 450. And it's going to give you a lot more information than I just did It goes back through all how to name acids, which is something we covered back in Unit 4, but it is something you're going to have to do in your book work. So if you need to review that, again, that page number is 450, and it goes all the way. It's kind of a long section, and again, you don't need to do the entire thing, but it goes all the way to page 479. But there towards the end, you'll see it talks about conjugate acids and conjugate bases again. So hopefully, if you need it, that will be another great resource for you. Okay, let me know if you need any help.